Hello, good afternoon and welcome. This short event, aimed to support students through our guided investigation series, the activity that was written by Peter Fox and who was also our presenter for this assistance webinar tutorial this evening. Good afternoon, Peter.
Good afternoon, Brian.
And I know you've showed me this activity before. I find it quite impressive, and I've tried this myself. Personal polynomials with TI-Nspire CX CAS technology. All yours then, Peter.
Thank you, Brian. So, personal polynomials, it's not something that we'd say is necessarily a practical application of functions, not something that you're going to use outside the mathematics classroom. I would label it as something more of a recreational sort of a thing to do. But there's nothing wrong with that. So let's kick off. The whole idea of the personal polynomials is that every letter in the alphabet is assigned a number. So A equals 1, B equals 2, C equals 3, and so on. And we're not worrying about any sort of case sensitivity. So it doesn't matter whether it's a capital A or lowercase a, its value is still 1. And what we do is every letter in your name is therefore replaced with that corresponding number. So someone by the name of Alex, that would start with a 1. Or someone with the name of Brian would start with the number 2, and so on. But we do that for each letter in your name. So the first letter is our first point. The second letter is the second point, and so on. So in Brian's case, the first point would be 1, 2. 1 for the first letter, and 2 because that first letter is a B, the second letter of the alphabet. And R, I think, is around about the 18th letter of the alphabet, so his second point would be 2, 18. And so it would be for the rest of his name. And your personal polynomial must pass through each and every one of these points. And that's how you generate it. Now, that's only just the introduction in terms of the first couple of parts or questions that you'll do in this investigation. There's a lot more to it. But what we're going to do in this session is demonstrate how to do some of these calculations. As an example, I will use my name. So to make life easier, I've just put some letters up on the screen. Your calculator, the TI-Nspire CAS, can actually convert these into numbers for you. So it's up to you whether you want to use the ASCII code that is built into the calculator to convert them all into numbers, or whether you just want to look at a chart like this. So, P, first letter is the 16th letter of the alphabet, so the first point that my name would need to pass through is 116. The second letter in my name, obviously, is an E, fairly quick and easy, so the second point would be 25. And the third point would be 320. So that's T is the third letter in my name, and it's the 20th letter in the alphabet, so that's the third point. And I think you get the general idea. So the fourth point would be 45, and the last one, R, would be 518. So now we have a set of 5 points. Let's have a look where those points might sit on an axis. Throw them over onto the axis, and it looks like a bit of a challenge to get a single function to pass through all of those. And when we say function, I'm talking about a polynomial. It would look something like that. So, could we solve an easier problem? Before coming up with that polynomial, is there a way we could just simplify this? Well, of course there is. We could just consider, say, the first 2 letters of my name. So if I was just considering the first 2 letters of my name, well, we could just do a straight line. Straight line equation, y equals mx plus c. Very simple polynomial of degree 1. And if I substitute in the first point for x equals 1 and y equals 16, we'd get a simple equation, 16 equals m plus c. Then, as I use the second point, 2, 5, I'd get another equation with the same variables, m and c, or parameters if you like. And now we're just solving some simple simultaneous equations, which would give us m equals -11 and c equals 25. And those numbers seem about right because our line certainly has a negative gradient and it's crossing the y-axis somewhere between about 20 and 30. So all looks good so far. But that's just PE. My name has a few more letters. If I included the third letter, that would make me a pet. But anyway, would get a quadratic. So if I'm looking at this as an evolving problem, 2 letters gave me a linear function, degree 1 if you like. 3 letters would give me a quadratic. So it seems that as I keep on adding more letters, 4 letters, if I was just Pete, an abbreviation, that would probably be cubic. And therefore, for 5 letters, I'm thinking we're getting up to a degree 4 polynomial, which is why when you start this investigation, your teacher may allow you to use abbreviations of your name, or perhaps your surname if it's a little bit shorter. I think if you only have 2 letters in your name, your teacher's going to add some in there for you, because otherwise we're trivializing much of this. So that's what my polynomial needs to look like. So let's see how we might do that. If we assume that it's a polynomial of degree 4, then I can set up a general equation, ax to the power of 4 plus bx cubed plus ex squared plus dx plus e. Now, in a moment, I will show you how to enter that in the calculator and how to set up these equations. But for now, we're just looking at, if you like, a by hand approach. So our first point, when we substitute that in, we're substituting x equals 1, in other words, p of 1. So we'd be able to state p of 1 equals 16. And when we do that, we get an expression or equation that looks like that. So I've substituted x equals 1, which would give me a plus b plus c plus d plus e equals 16. One equation, 5 unknowns. If I substitute in my next point, that is p of 2, that would give me an expression or equation that looks like that. So now we have 2 equations, still 5 unknowns, and I think you can see what's happening here, as we put our third equation, or our third point in rather, I get another equation, the fourth one in, and then the fifth one in. So now I've got 5 equations and 5 unknowns. Now, if you were to proceed by hand with this, you'd be doing simultaneous equations, much like I did with the linear one. And a simple letter to get rid of here would be E, because there's only one of them in each one. So if I looked at just the first ones, P of 1 and P of 2, I could do P of 1 minus P of 2. And that would allow me to eliminate E. So now I've got an equation with just 4 variables, A, B, C, and D. I could do a similar thing with equation 2 and 3. So I do P of 2 minus P of 3, just systematically working through this. That would give me a second equation with 4 variables. Then I could continue on using P of 3 minus P of 4, again eliminating E. So now I've got 3 equations with 4 variables. And then P of 4 minus P of 5. And now I've got 4 equations, 4 variables. So I've gone from 5 equations, 5 variables, and to 4 and 4. And so I could continue. That's what my 4 equations look like. And that would be appropriate to eliminate D. And so you could proceed and eventually get down and work out what A is. Now, there's a couple of other ways we can proceed here if we don't want to use simultaneous equations by hand. There's a lovely other technique we could use. That is, wrap all of that information up into a matrix. What I've done here is just look at the coefficients and put them into an array, if you like, consisting of 5 rows corresponding to the 5 points and the 5 equations. And the last column you'll see there corresponds to the y value for each point. if you put that into a matrix, there's a lovely little tool on the calculator called row reduction in echelon form. And that will spit out some answers for you. That looks something like that. So that would tell me A equals 4.7, B equals 56.83 something, and C equals 235. So it actually solves the equations for you. But if you want to do things, let's say, purely using CAS, you can use the solve command, which is what we're about to do. So it's probably time we jumped onto the calculator. Let me bring up my software. And we'll start by defining our function. Define. I'm just typing these things in because it's fairly quick. It could be P for polynomial or P for PD here. Now make sure you use the multiplication sign when you're entering these things in. So I've got ax to the power of 4 plus b times x cubed plus c times x plus, oh, I missed a squared there, plus dx plus e. So again, where did my equations come from? We said P of 1 equals 16. So that was the first equation that you saw before. P of 2 equals 15. Sorry, no, it doesn't. It equals 5. E is the fifth letter of the alphabet. Now, if I was doing this using a sort of by hand approach, I could do something like saying equation 1 is equal to this thing, and equation 2 is equal to this bit. And then I could do equation 1 minus equation 2. And that was how we're doing it in that sort of by hand approach before. And then you could do the same thing with P of 3, P of 4, P of 5, and keep on eliminating the variables one at a time like we did before. But there's a quicker way. Oh, and of course you could do the row reduction echelon form, which was kind of shown up there before. But there is the other option. That other option being just using the solve command. Now there's two ways you can use that. You could just say solve P of 1 equals 16 and P of 2 and keep on typing all of those in. But I'm going to take you into the menu and we'll have a look at what other solve tools are available to us. So menu, algebra, and we see there's an option to solve a system of equations, option 7. Solve system of equations, and these not linear, it's option 1. And how many equations do we have? We have 5 of them. Press tab. Tab's a great way to navigate through here. And our variables in this case are not x and y, but a, b, c, d, and e. And it tells you that each variable must be separated by a comma, which I've done, and press enter or tab down to OK, and it sets up a template for us. Solve, and all I need to do is type in the bits that I know. So my first letter of my name, so 0.1, P of 1 equals 16. Now you can just arrow down or tab down. P of 2 equals 5. P of 3 equals 20. P of 4 is back to the 5 again. And P of 5 rather, which is the R, R is the 18th letter of the alphabet. And so it's done. Well, if that's all we had to do in the investigation, we'd be wrapped up in 15 minutes and no need to go any further. But that's not the case. There's a lot more coming. And we also need to graph it. Now, it'd be kind of nice if the calculator would automatically store all of those values in A, B, C, and D. It doesn't, but you can arrow up, select the first bit, and if I want to assign it, just put the little colon in there, and then I'll go up again, I'll grab the second one. So it's a little bit time consuming. There's a neat way if you're using the matrix approach. There's a neat way to do it there. I probably should have arrowed from the left there, but never mind. I've almost got them all. If your name has 20 letters in it, you're really going to beg for your teacher to reduce your name somewhat for an abbreviation. And we have one letter to go, and that's our E. E is equal to 223. So my personal polynomial is that. How beautiful is it? If I want to have a look at it on a graph. So I'll do Control I, it's a nice keyboard shortcut, and Option 2, insert a graph. Now if I just put P of X in here, the window setting is not going to be great, but let's just put it in anyway. P of X. So it's all kind of squished up. Polynomials of degree 5, they tend to take off pretty rapidly. You raise a number to the, polynomial of degree 4, you raise the number to the power of 4 and it gets big pretty quick. But let's think about the sorts of things. We could drag and manipulate the screen, or I like the idea that we're going to think about what values we might want to show. So I'm going to select window settings. Now, my X values go between 1 and 5. I could just set the window to that, but I want to see a little bit to the left, so I'll go 2 units off to the left of my smallest X value, and let's say 2 units to the right of the largest one, so -1 to 7. Scale of 1 is appropriate. In terms of the Y minimums, it's kind of a guess to start off with, but knowing that raising a number to the power of 4 is pretty big, but also knowing that a lot of those points are hovering around, between 1 and 26, obviously, I think -20 would probably be okay. And I'm going to search all up to about 100. And if I'm doing a scale that encompasses 120 units, I think a Y scale of 20 for the little hash marks would be appropriate. So there's my graph. Now, depending on what parts of the task your teacher wants you to do, you may be asked to use, you may be asked to use the bisection method to find out the axis intercepts. Well, not for the y-axis, but at least for the x-axis. We already know what the y-axis intercept is. That was our value for E, 223, I believe. So there's a couple of spots. There's one that looks as though 2 in between 1 and 2, and it looks as though it's almost tangential to the axis over here, but we could zoom in. You can do menu, window, zoom in, or zoom box. I'll do a zoom box, and let's have a look at this little region here. And I can see I've got 2 axis intercepts there. You could trace, but you can also solve. So this will be a numerical solution, and that's why it's good to look closely at the graph, because there's no analytical solution here. It's a numerical approach, as I say, the bisection method that the calculator is going to use to find out where these points of intersection are. So for here, I'll choose Analyze Graph, and you can see the first option, find a 0, put a left bound and a right bound, and we get 1.4119, and the other one's going to be a little bit more than that. Now, if I want to go back to the previous window setting, the one I set up, Control Z is a lovely way to exit back out of where we were. That undoes the 0, and Control Z will return back to our previous window setting. So that's how we can find our equation and zeros. And of course, another way to find zeros is just solve P of X equals 0. Solve for X. You'll see the first solution, the 1.4119, the one just to the right of it, and the other 2, very, very close together. But remember, use the graph, because if they're really close, it's possible to miss one using these numerical approaches. So always come back and have a look at the graph. And that's not just for personal polynomials, this task. It's for almost anything you do. Always worth looking at the graph to see if things make sense. Question, can we find exact values from the graph? Not specifically, because it is a numerical method that we're using to find those solutions. We can, however, check to make sure our equation is correct. P of 1, for example, gives us 16. P of 2 gives us 5. If I'm in the graph application, you can press Control and T to toggle on a table of values and see that, yes, we're going through all the points that my polynomial is supposed to go through, 16, 5, 25, and 18. And if you want to, you can toggle that back off, Control T, and it will go away. So, row reduction, echelon form on a matrix is handy, solve command is handy, simultaneous equations, all of those will help you work out your equation. But does that always happen? So my name, Peter, has 5 letters. We went to a polynomial degree 4. So in other words, Brian's name, that has 5 letters. Is his a polynomial degree 4? What about all names? Like if it's got 6 letters in it, does that mean it's a polynomial of degree 5? Do we just subtract 1? Let's find out. I'm going to explore my second name, Fox. There's the letters in my name, represented as points, 1, 6, 2, 15, and 3, 24. Now, alarm bells might start ringing straight away because they're equally spaced in that diagram. Indeed, if you try and work out the polynomial for that one, you'll see that it's a linear function because it goes up by the same amount each time. I increase from 6 to 15 is an increase in 9, of 9, and 15 to 24 is an increase of 9, so it's actually a linear function. So there are some names where you don't need such a high degree polynomial, and you'll have to see what happens when you use the algebra to explore that. Elon Musk, E-L-O-N, that's 4-letter name, but I think you'll find he might be able to get away with something like a quadratic instead of a cubic. So they're things to look out for, and you need to see if you can find other names that share that property where you don't just subtract 1 from the quantity of letters to come up with the degree of the polynomial. All right. Other things we're going to have a look at. A good friend of mine has a daughter by the name of Ava, and that is an interesting name because it's palindromic. Now, as it turns out, Ava gives us a quadratic. It's got 3 letters. We subtract 1, we get a degree 2 polynomial, a quadratic, but that one's actually quite easy to work out. Just like Ava's name being palindromic, symmetrical, same forward it is backwards, that means we're going to get similar properties with our polynomial. Well, a quadratic is symmetrical about a line through its turning point. So it's fair to say that when you come up with that quadratic equation, it's going to have a turning point at 2, 22. What about Asa? Asa is also a palindromic name. And if we go back to our idea that we had before, and that is it's got 4 letters, take 1 off that power, that gives us 3, or 1 off that quantity of letters, that gives us 3. So do we have a polynomial degree 3? Well, as we just mentioned, Ava has symmetry about her because her name is palindromic. So does Asa. His name is palindromic, so we would expect some symmetry about his name as well, and therefore about his polynomial. Well, cubics are not symmetrical about a line. They have rotational symmetry about their point of inflection, but that suggests that maybe Asa is a quadratic because he has symmetry about his name. So that's why you'll find that there's lots of questions about palindromic names in the actual investigation, but you can still use exactly the same approach as what we did to explore my name. Start by defining it as a cubic and see what happens. That's part of the idea of an investigation. All right. What about Andrea and Andrew? How often do they meet? But perhaps equally as important is, do we really have to go out and figure out what their polynomial is to answer that question? Well, let's have a look. I know that, say, for example, Andrew, his first letter of his first name is A, and so is Andrea's. So they will both have the point 1, 1 in common. Indeed, they will have their second letter in common. So I have 2 points of intersection for Andrea and Andrew already. They both have to pass through 1, 1. They both pass through 2, 14. Indeed, they'll both pass through 3, 4, which is D, the third letter, fourth letter of the alphabet, and R, and E. So the only question remains is, if you were doing their name, now they've got 6 letters in their names, polynomial degree 5, we've got 4 points of intersection already. Is it possible that they would have 5 points of intersection? Think about what's happening in Andrea's polynomial. Once we get past the E, the polynomial is going to come back down and loop through the A, whereas Andrew, it takes off. So the question is, will they intersect again after the point 5, 5? And do I need to work out their equations in order to answer that question? So, what about names that don't have a solution to P of X equals 0? Think about how their letters might be positioned on the Cartesian plane. Let me just jump back onto the graph here. My name, the E, is actually quite low. It's fairly low in the alphabet in terms of the number. So names that have a lot of letters up here, let's just say past the middle of the alphabet, may not extend down below 0. So you could just randomly choose names. But when you start thinking about the shape of the parabola, or the shape of the polynomial rather, you can start to rule out names pretty quickly about the ones that are likely to cross the axis. Any name with an A in it, for example, highly likely to cross the axis. In fact, you should be able to think of some 3-letter names that definitely won't if you think about their first and last letter and their middle letter, where their turning point might be. So, hopefully, you've got a few ideas on how to proceed with this investigation. At the very least, you've seen how to determine your own personal polynomial, and the rest of it is up to you to explore. There's lots of questions in the task to guide you through, but you've got the basics and you've got the essence of what we're all about. So, we're pretty much out of time. We said 30 minutes. I think we've pretty much nailed that. Brian, did we have any questions from our participants that we need to jump through?
Thanks, Peter. You did address a couple that I fed through to you there, so thank you for that. I was just starting to type into the chat I'll keep the event open for a couple more minutes in case students wish to ask you questions directly. A reminder that they type into the chat box down to the bottom right and to direct the question to all panelists. That way Peter and I will both see them. So thank you again, Peter. A very inspiring activity there, excuse the pun, and I think it really gets to the heart of a lot of the important understanding for polynomial functions, which we know are so important for the Maths Methods course. I'll bid you all farewell and thank you for joining us.